12 marks on a round of dough. 1 pass of the pin, coming down now. 2 of these will come through pointing exactly where they started. Quick, which 2? You can't, neither could I. Nobody picks them, the dough does. And those 2 lines rank web pages, tell you when a bridge will shake itself apart, and set how long a drug stays in your blood. So, is there anything this press doesn't turn? Take one of the 2 that held, and turn it slowly, all the way round. Most of the way round, the mark comes back, pointing somewhere else. The angle between them is the thing to watch. And twice, only twice, that angle falls to nothing. Those 2 directions, the press cannot turn. It can only make them longer, or shorter. 1.8 times longer here, 0.56 times there. The direction has a name. It's called an eigenvector. The number has a name too. It's called an eigenvalue. And that is the whole of it. A, V, equals lambda, V. Flour, worked deep into the boards. Red, mixed in a shallow dish. Every board on this bench has a grain. So does the wheat, long before any of this begins. And you can't find a grain by looking. You find it by pressing. Which way does it stretch most? Point the mark anywhere you like, and ask something simpler. How much longer does it come back? Plot that as a height, for every direction at once, and you get a ring. Run round it. The height climbs, falls, and climbs again. And the highest point on the ring, 1.8, sits exactly on the grain. That's a definition, not a coincidence. X transpose X, divided by X transpose X. Now drop to the level of the bench. The 2 peaks face each other, dead opposite. Rise up and look straight down. Peaks and troughs, 90 degrees apart. Press straight down with a flat pin, and the 2 grain lines come out square. Not usually. Guaranteed. Wider one way, and thinner the other. The sheet outgrows the board it's on. Thin enough, now, to see the lamp straight through it. And before it was ever a sheet, remember, it was a ball. So score a small square into it, and press again. How much dough? After, start with the ball, and press it once. It comes out an ellipsoid. Its 3 axes are the grain in 3 dimensions this time. 1.8, 1, 0.56. Multiply those together, and you get the volume. 1, exactly 1. Stretched one way exactly as much as it thin the others. That product is the determinant. The factor of volume gets multiplied by. Sight down the shortest axis. The other 2 are square to each other. Now press that 3rd axis all the way down to nothing. A solid becomes a shadow. The volume reads 0, and there is no rolling that back. Back to the flat square, and its 2 stretch factors, 1.8 and 0.56. Turn a measuring frame right the way round. The 2 readings never stop changing. Their sum never changes at all. 2.36, from any frame you like. That sum is the trace. And you never had to find the grain to know it. But not every press is a kind one. So flip the whole sheet over. Or hold it up to the lamp. And press it out completely flat. Stack the sheets up square. Then slide the stack sideways. Or take hold of the round. And simply turn it. So does every map have a grain? Same instrument, 4 presses. Watch the angle. The turn, first, run the mark all the way round. The angle never reaches 0. Not once, anywhere. There's no direction, this leaves alone. Both eigenvalues have left the real line altogether. 0.8253, plus and minus 0.5646. Length 1, and an angle of 0.6. A turn, wearing a number's clothes. The flip, 0 twice, so 2 grain lines, but 1 length comes back negative. +1 and -1, the same line, pointing the other way. The shadow, 0 twice again, and this time one of the lengths is 0. everything in that direction is gone. The determinant is nothing, and nothing brings it back. And now the slide. Same instrument, one last time, all the way round. The angle touches 0 once. There's one grain line, and the eigenvalue on it is 1 twice over. So where is the second? There isn't one. Not hidden. Absent. No change of coordinates will produce one. Not ever. Most of what's hard about matrices lies right here. Now roll the whole thing out again. Thin. Fold it over in 3. Roll it out flat. And fold it again. 6 turns of that. Then take a knife to it. And look hard at the cut edge. And if you do it again. 3 layers. 9, 27, 81, 243. 729 out of 6 folds. 1 stretch, applied over and over. A to the k equals v, lambda to the k, v inverse. The grain doesn't move, only the numbers sitting on it grow. So put every mark back, and press, and press, and press. They're all swinging the same way now. The biggest eigenvalue eats everything, at a rate of the second eigenvalue divided by the first. One caution, and it's an honest one. The roll is the eigenvalue. The fold is not. Folding is where this stops being linear algebra and starts being chaos. Leave the bench a moment. A carved block, inked and ready. That small notch at the corner is a registration mark, so no color layer can slide against the one beneath. Miss it, and you get this. 1 layer, shifted. A misregistered proof is a shear, with a name and a cause. Anywhere a thing feeds back into itself, a room, a rumor, a population, the biggest eigenvalue, decides whether it fades or runs away. And where things drain instead, the slowest eigenvalue owns the tail. 2 exponentials added, the fast one vanishes, and what's left goes straight. That is why a plasma curve is a sum of exponentials, why the macro constants alpha and beta are the eigenvalues of the rate matrix, with the minus sign taken off. And why terminal half-life belongs to the body and not to the dose. Peel it up. The grain was never about dough. It's about what a thing can only stretch. 1 pass of the pin, that's A. The mark that held, that's V. How much longer it came back, that's lambda. The square you scored, the determinant. Any frame you like, the trace. The stack that slid, defective. And the folds, lambda to the k. Same bench and the same lap. 12 fresh marks, laid down at random. Only this time, before the pin comes down, you already know which 2 will hold. Find the grain, and the map stops turning. It only multiplies.